Hello and welcome to the 17 Quantum Starter course. So this course is actually meant to give you an overview, a launchpad into the awesome world of quantum computing. And as you all know, 17 Quantum is committed to democratizing knowledge of quantum computing, quantum mechanics, and this is our introduction to the subject to all of you. So think of this as quantum computing and quantum mechanics 101 for newbies. So without further ado, we'll dive straight into the course. It's going to be a beginner's guide to quantum mechanics. And in the course of doing this, we're going to look at certain things. One of them is what exactly quantum mechanics is, what the rules of quantum mechanics are, how quantum mechanics is going to shape our world, or how it's already shaping our world, as it were, and what the future of quantum computing is going to be. Um, we'll dive straight into it and just listen very closely, as this will be the foundation into most of the other courses, all the other modules that our faculties are spending quality time to develop. So, what exactly is quantum mechanics? Um, as a prerequisite to understanding the subject of quantum computing, it's really important that we understand the foundations, which is quantum mechanics and how it came to be. And I would just like to take us through a very simple journey of Isaac Newton, the apple, and classical mechanics. You see, classical physics is the physics of the very large. So from planets to balls to apples to cars and shoes and everything that is not microscopic scale, right? And at that scale, we can easily predict, positions, motions, speeds, velocities, and so on and so forth. So you can calculate the trajectory of a projectile, for example. This is super intuitive, and if there's anything you know about physics, this is it, right? That it's something that is based on fundamental mathematics that is very predictable. However, Max Planck came and a lot of things changed. The intuitiveness of physics disappeared, and we began to have concepts like the wave particle duality. So, what that means in simple terms is that light, as we know it, behaves as both a wave and as a particle at the same time, right? And that is the wave particle duality. Quantum mechanics is built fundamentally around this concept, right? And Einstein came along and formalized that theory that Planck started. In the next few pieces of the course, we are going to look at how Max Planck, came about this, right? A couple of things were discovered around the birth of the 20th century from the late 19th century. And one of those things was ultraviolet catastrophe, right? So there's something called a black body, and a black body is any object that is very, very hot, super hot, so hot that it emits some form of radiation. For example, sunlight or a hot ion, anything that is hot essentially, all right? And the theory at the time was that as the heat of objects increase, the frequency of light they emit also increases. So as objects get hotter and hotter, the color of the object changes from red to yellow to blue towards the ultraviolet. So that was the understanding of physicists at the time. However, experiments showed that that was not the case. You had the sun, which was obviously not blue and ultraviolet, and there was a quandary to understand why objects were not complying with the theory at the time, which was the theory that was based on classical physics. It wasn't until Max Planck came along and discovered that light, a beam of light from a torchlight, is actually not a continuous flow. So a beam of light is unit packets of light. So think of it as pouring out grains of rice from a bag of rice. It seemed like a continuous flow from a distance, but if you look closely enough, it's actually grain by grain of rice pieces. So similarly, light is actually made of packets, units of light by unit of light, which we call the quanta. So quanta was the birth of quantum mechanics. This was Planck's big discovery that resolved the issue with the ultraviolet catastrophe. And applying quantum mechanics to ultraviolet light and black bodies showed that indeed they shouldn't turn into blue objects as they get hotter and hotter. Rather, they should emit some heat and behave exactly as you know it in reality. Another very interesting thing that Einstein discovered in 1905 that led to his winning of a Nobel Prize, and of course that led to having solar panels on your roofs today, is the photoelectric effect. Einstein discovered that if light falls on certain metals like tungsten, um, it's able to pump out electrons from the atoms that make up those metals, and those electrons flow through the metals and conduct electricity. So what that means is for electrons to move, light has got to be a particle that can knock off electrons. This was an epiphany like the days of Archimedes, bigger than the discovery of sliced bread. And indeed, Einstein called those light packets that are able to knock off electrons photons. And the phenomenon came to be known as photoelectric effect. As you may have imagined, this is applied across industry, and this was, of the 5 papers that Einstein published in 1905, this was the singular paper that won him a Nobel Prize and is the basis of solar technology today. Another really interesting thing that also happened around the turn of the 20th century is a double slit experiment, right? So scientists found out that if you have think of a cardboard paper with 2 slits on it, right? And I'm going to move to show what that looks like, right? Think of a cardboard paper with a slit on it, and you are shooting, and then you have a particle gun like a marble machine, right? Shooting particles through the slit. What you find on the back of the slit is an image that mimics the slit, right? So in this case, because it's a single slit, you find a single line as image behind the slit. And if this is a particle, even when you increase the number of slits, what you find behind the cardboard paper or on the board, right, should be the number of slits that you have on the cardboard. And you see exactly this. However, this is on the assumption that light is indeed a particle. But then the reality on ground was when scientists put a double slit in front of light and they don't observe it, what they find is that the patterns on the board behind is not the same number of slits that you have in the cardboard, which was profound beyond imagination. So you can imagine how perplexed scientists were at the time, because you have 2 slits, just double slits, and you have multiple interference lines on the board behind it. And scientists began to ask questions, as they always do. Why do we have this kind of phenomenon happening? And this became known as the double slit experiment. There was one and only one explanation for this. The explanation was that light was actually a wave. And think of water waves, right? When you drop a stone inside a pond, you have the ripples that come out of the pond. If you drop 2 stones simultaneously into a pond, what you have is the waves or the ripples from the 2 stones canceling out at certain points where they interfere, right? And those are interference patterns that we find in waves. So similarly for water, when you have 2 slits, so 2 slits is akin to dropping 2 stones simultaneously in a pond. And what you have are interference patterns that continue outward. So they diffract outward and they land on the board, and you see them as those patterns, multiple lines but those lines are actually interference patterns from the waves that were created by light, as opposed to particles that we have always understood in classical physics. This is a revelation of the magnitude of Nostradamus, right? And it changed the course of history. It changed our understanding of reality. It changed the trajectory of physics, and it's known as a double slit experiment. There is no other conclusion you can make from this experiment other than light is actually a wave. Particles do not create interference patterns, right? And it's very important that you understand this as we go on. So I ask you a question, ladies and gentlemen. Do you still think physics is as intuitive as you have always known in classical mechanics, in F equals ma, and force and mass and acceleration and so on and so forth? Well, maybe not exactly. So quantum mechanics is the other side of physics that is not as straightforward as classical physics, right? There are strange rules that govern quantum mechanics, but they would only be strange before you took this course. At this point, we will demystify a couple of these strange rules, and you'll be ready to actually understand the rest of the course and the gigantic machinery that is being built around the concept of quantum mechanics, that is already set to change the course of human history forever. So one of those rules is the principle that Werner Heisenberg, a German scientist, in 1927 discovered, and that principle is known as the uncertainty principle. What that principle is, in simple terms, is this: if you throw a stone, or if you throw a piece of sweet, right, or candy or gummy, whatever it is, you, using the laws that Newton formulated, will be able to predict at every point in time where that candy is and the speed with which the candy is traveling in space and time. However, in quantum mechanics, not quite, right? Not exactly. You can't predict the position and the speed of subatomic particles at the same time. It is forbidden. What you can do at best is estimate probabilities of the particle occupying certain positions in space and time at every given point in time. So it's, again, not intuitive, but this is very important that you understand this. This is one of the cornerstones of quantum mechanics. It says that you can only have a cloud of probabilities around subatomic particles, right? You can never be very accurate. In fact, there's a formula around this saying that the more you know of the position of a particle, the less you know of its speed. And the more you know of the speed, the less you know of the position. So you can never, there's always an uncertainty. It's always probabilistic. Life is no longer as deterministic as you have always known it. You can't predict everything, right? And this is known as the uncertainty principle. And another, just before we move on, there's also another rule that is really interesting called superposition in quantum mechanics. So superposition is a rule that says that those electrons that you have in the electron cloud, the probability cloud that we just described under uncertainty principle, the state of every electron at every given point in time can never be known. You can only guess, and those are probabilities, right? So, but at that point where you are guessing, it is assumed that the electron has multiple states at the same time. So think of it like this: an electron is occupying a point in space, and you say, oh, there's a 47 probability chance that the electron is actually occupying that point. But then there is another point in space where the electron is also occupying with a 30% probability. In physics, we assume that the electron is occupying all those states put together, combined in a linear combination at the same time, simultaneously. So this is called superposition of multiple quantum states of the electron. Now, this is very important as you dive into the world of quantum computing, because the cornerstone of the fundamental particles that run on a quantum computer are always in a state of superposition. So you really have to get this. So every electron, every subatomic particle occupy multiple states simultaneously until, and now listen carefully, until a wave function collapses, or until you are able to collapse all the states into one and you actually determine where the particle is. And in a minute, let me just go back to Heisenberg's uncertainty principle. It says that you really can't know where the electron is at any point in time, right? In the double slit experiment, the electron wave diffractions formed interference patterns that hit the wall behind. The interesting thing about that experiment is in the situation where an observer is watching the light go through the double slit, it forms only two interference patterns behind. But when there is no one observing, it forms multiple interference patterns. This is just weird, right? But quantum mechanics is weird. Nobody really understands it, right? So if you are watching the experiment, it forms two patterns behind the cardboard. If you are not watching, it forms multiple interference patterns. What that means is the act of observation affects a subatomic system, a quantum system. So for quantum superposition, which is coming back to where we are, the electron occupies multiple states simultaneously. However, the moment you observe the electron, the wave function collapses and all the states collapse into one, and you have a single position where you can observe the electron at that point in time, right? So just keep this at the back of your hand and we'll understand better as we go on, right? So there's something I put here. So if you want to think about superposition better, just think of flipping a coin, right? So once you flip a coin, while the coin is swinging in air, it is rotating between heads and tails simultaneously, right? So you can neither say whether it's a head or a tail. As a matter of fact, it's in a superposition of two states, 50% head and 50% tail. But the moment the coin drops and you catch it, only one phase shows up, and that is the collapse of the wave function. You're able to say, yes, the coin is either head or tail once you catch it, right? So that is what I'm trying to say, that if you observe the quantum system, it collapses the state into one thing. Now, this is profound beyond measure, right? It's crazy, right? It gives you the opportunity to do multiple things at the same time. As a matter of fact, you will understand later that quantum computers are powerful as they are because they are allowed to do multiple things at the same time. Your normal classical computer can never do multiple things at the same time. You see, this is very interesting because one of the famous scientists in Germany at the time, Erwin Schrödinger, came up with a thought experiment, and he was like, imagine you have a box, a cat, a radioactive atom that has a 50% chance of decaying, and a Geiger counter, right, that can count when a poison is emitted from the radioactive bottle. Because the radioactive bottle has, or radioactive atom has 50% chance of decaying, it means that it could decay and it could not decay at the same time. It's occupying a superposition of two states, right? If you close that box and you don't observe it, quantum physics teaches us that because the atom is in two states, which means it has both decayed and not decayed, 50-50, it means the cat that is there has inhaled the poison and has not inhaled the poison at the same time, and it means the cat is both dead and alive at the same time. So the Schrodinger's cat experiment is saying that until you open the box, the cat is both dead and alive at the same time. This is the world of many possibilities. If you want to live forever, you should be thinking about bringing quantum mechanics into life, because it means you can both be alive and dead simultaneously, like the Schrodinger's cat, which I don't know what that would mean for the world, right? The next and the last thing I would like to talk about, the rules of the strange world of quantum computing, is quantum entanglement. You see, there's a Chinese legend called the red thread of fate. And the legend states that every two human beings who are destined to connect, who are destined to come together in contact, are connected by a red thread. So I don't know how the Chinese came about with this, but in physics, this is akin to something we call quantum entanglement. So quantum entanglement is a phenomenon where you have two subatomic particles and they are somehow connected. We don't fully understand the connection yet. But if you take one to one part of the world and take the second one to the other end of the world, whatever you do to one of the particle is reflected in the second particle. In fact, some people believe that this is the explanation behind the phenomenon of love in human beings. And Einstein called this spooky action at a distance. So what that means is that from a distance, if one of the particles is heads, the other one is tails. And once you switch the heads to tails for one, the other one switches automatically, and there is no connection. And this interaction is faster than the speed of light, faster than anything you can ever think of, faster than you lift your hand from a hot stove when it burns you, right? So it's an interesting piece of reality in physics that none of us, Niels Bohr, Einstein, nobody really understands, but it happens. And it's also one of the cornerstones of quantum computers that you really need to understand at this point. So, how is quantum mechanics going to shape our world? Honestly, in so many ways. Just for starters, I would like to tell you that the sun is only burning because of quantum mechanics. At the core of the sun is a phenomenon called quantum tunneling. And that phenomenon is simply whereby you have hydrogen atoms fusing together. The sun is just a big bomb, right? It's just a big fusion bomb. And you have these hydrogen atoms fusing together and generating heat and light as a consequence. But the interesting thing is, those atoms do not have enough energy to be able to fuse together, yet they do that. This is quantum tunneling. It's a phenomenon whereby you have a ball on one side of a wall, and somehow you strike the ball to the wall, and the ball magically appears on the other side of the wall without having enough energy to actually penetrate through the wall, right? And this happens in the subatomic world every now and then. You have electrons passing through barriers that they don't have enough energy to pass through normally, right? So without this, the sun would not work. And let me blow your mind. You see, the AI and the big computer chip companies would not also be in existence if quantum tunneling does not happen, because at the very, very microscopic chip level in the motherboards, quantum tunneling is happening every now and then in transistors, in semiconductors, integrated circuits, right? So you owe a lot to quantum tunneling. And if I were you, I would give a round of applause from wherever I am. There are also other everyday quantum effects that you have as a result of quantum computing. For starters, quantum computers basically run on qubits. So you have the classical bits, which can occupy zeros and ones for normal computers. For quantum computers, you have quantum bits, and they can occupy multiple states at the same time. They can run thousands of millions of calculations simultaneously, unlike your computer that runs one at a given point in time. And what are the two rules that quantum computers depend on? You have definitely must have guessed it right. They are superposition and entanglement, right? And like I had said, solar panels only work because photoelectric effect is possible, which was discovered by Einstein as a byproduct of quantum mechanics. And that is one of the big implications of quantum mechanics on everyday life. And the sun as well, the sun that gives us light and food, because without the sun, plants cannot even grow. And the sun is burning because quantum tunneling is possible, because subatomic particles can overcome barriers that require more energy than they actually have, right? And at the core of the sun, this is what happens, right? So the future of quantum computing is bright and is big, a lot like the future of AI today. Quantum computing is still at its nascent point, but it's definitely got a lot of stake in our future, and it's important that we understand this, at least at the basic level. One very, very quick one is quantum teleportation. You see, as a child, I've always been fascinated by the idea of traveling in time into the past or the future, or traveling from a point in space to another point in space without an airplane or a car. And this can be made possible via a phenomenon called quantum teleportation. If you have watched sci-fi movies, you would have seen where wormholes are created and you're able to go through wormholes and appear at other points in the world, from China to Malaysia, from Malaysia to Ghana, from Ghana to Calabar, or any part of the world, as it were. With quantum teleportation, this could become reality. We don't yet have these machines, but there are a lot of theories that have been propounded around how these machines can work. And thanks to quantum entanglement, this is something that is being thought out in reality by engineers. And hopefully, one day within our lifetime, we would have machines that would leverage on quantum teleportation to move us from one point in space to another point without an automobile. Another very important one that is closer to home than you think and closer than quantum teleportation is a quantum safe world. Today, quantum computers are being built by the big tech. We have the Google, the IBMs, the B companies, Xanadu, building giant quantum computers. And what that means is a lot of things that we thought were immune to attack would become very vulnerable. And the quick one is our encryptions. Our banking encryptions are based on something called the RSA encryption. And what that means in simple terms is they multiply two big prime numbers and get a single number that they encrypt your systems, your banking systems with, that you can't easily factor into the prime numbers that made it up, right? So the difficulty in breaking the system relies on the ability to break that big single number into the two prime numbers that makes them up. And if you think about the length of the digits of these numbers, hundreds of digits, you will understand how difficult it is. No classical computer today can break those numbers in less than thousands of years. So nobody even attempts it. But with quantum computers, because superposition is possible and those computers can run multiple operations simultaneously, this can become possible. As a matter of fact, it has been shown to be possible. Quantum computers can break banking encryptions easily and seamlessly. What does that mean for us? For starters, it means you shouldn't hand quantum computers to kids. But beyond kids, it also means that we have to upgrade our encryption systems in banks, in the financial industry, in different industries where we have different levels, different tiers of encryption. We have to upgrade them to more robust encryption, quantum proof locks, right, that are safe from quantum encryption interferences, right? And I'm pleased to announce to you that there's a lot of work that has happened in this area, actually. Some companies have come up with quantum locks that depend on what we understood from the double slit experiment, right? So they transfer bits and bytes of data, and your attempt to interfere with those data and decrypt it alters the data itself. Just the same way your attempt to observe a quantum system in the double slit alters the outcome of the double slit experiment. So it becomes practically impossible for you to break the encryption, because trying to break it changes what the encryption itself is, right? So these are quantum safe systems that are being developed, essentially locks that no matter how good you are as a lock picker, you cannot pick, right? And we're getting to that point in the world where we'll have systems that nobody can break, and that will be all thanks to quantum mechanics and quantum computers. So, ladies and gentlemen, this is a preamble into the very fundamental concepts of quantum computing. The rest of the courses on the platform will leverage the knowledge that we must have gained in this starter course. And at any point in time, you can always reference this course and drop your questions in the community, in the chat section. And the team is always on ground, the community is always on ground to respond. And I can assure you that it's a thriving community that is here to help you grow and help you on the journey into quantum computing. And 17 Quantum will lead you on that journey. So thank you so much, and see you in the next course. Thank you.